virtue of the fact that they believe in Tesla and they're excited about Tesla technology and Tesla coils as much as I am. First, to my left, Mr. Tony Chillemi. How many people in the audience here are amateur radio operators? Raise your hand. All right, look at that. I love it. Kilo Delta 6, India Foxtrot Charlie, KD6IFC. Now I'd like to introduce his better half. He's going to kill me for saying that after this. Rosalie Sorrell, the electric lady. She's going to be a part of our demonstration phase this morning. Her call, Kilo Delta 6, Kilo Sierra Golf, KSG. Well, I know it by the phonetics. You know, everybody has phonetics for their call signs. I won't tell you what hers is, but it's KSG on the suffix. And if you know that I'm a ham radio operator, I'm N6UXW, and I call my home QTH RF Gulch. The reason why I call it RF Gulch is not because of the Tesla coils. We have an AM radio station that's about 1,500 yards from where I live as the crow flies. They use a 5-element phased array 3/8 lambda antenna system fed by 50 kilowatts of modulated AM RF. So I have a field strength in my backyard of over 10 volts per meter, 24 hours a day. Now, that in itself is not bad, as far as I'm concerned. All this controversy about electromagnetic radiation is needing a lot more scientific investigation and quantitative study, and that's my statement on that. But at 10 volts per meter, you can imagine trying to run a Wheatstone bridge or an impedance bridge. Measure the inductance of a coil? Right. Get a Faraday cage, because you can't do it with that kind of a high field system running in your backyard. What I want to do today, ladies and gentlemen, is I want to talk about several things. Having introduced my guests, I also need to tell you that they stayed up 24 hours round the clock to help me finish this base unit, which wasn't even tested here until last night. I'm happy to report to you that it works fairly well. And I'd like to thank them and all of the people back home who I didn't bring with me who also assisted. What about Tesla coil technology, and what about spark gap design, and what about what you've read in the paper, the nonlinear relationship of voltage versus spark length from a Tesla coil? I want to address all of these things, so you're going to have sort of a potpourri of topics being covered. We'll cap that off with a live demonstration. I'm sorry for the view graph here not being better visible than it is. All I've done is put that up to indicate that I'm going to cover these different areas of the presentation. Most of you, of course, are familiar with the general theory of operation of a Tesla coil. And the coils that I build and work with are strictly spark gap driven pieces of equipment. So there are several things regarding a Tesla coil which are categorically true. Simple math, L sub 1, C sub 1 approximately equal to L sub 2, C sub 2. That's the relationship of a tuned radio frequency transformer for which Tesla holds the pioneering patents. Another thing is, just like with you ham operators who would load up on 40 meters or 20 meters, what are you doing? You're creating a proper inductive, reactive, and capacitive reactive load to match your transmitter. So you have what is called a low VSWR, or voltage standing wave ratio. That implies that where the coax meets the antenna at the amplifier, or the linear, or the output of the transmitter, the current is at a maximum. And out at the end of the antenna, the radiating element, the voltage is the maximum, or you have a maximum VSWR. Tesla coils are no different. They're just like any antenna system. Only in the case of a Tesla coil, it's a lumped inductance in the form of a helix or a flat spiral winding, as opposed to being a long, straight radiating element. So another thing that is important about Tesla coil design are some of the relationships that we need to look at. To begin with, you see here what looks like a standard Tesla coil circuit. On the left is a power source, typically a 60-cycle transformer. The high voltage capacitor, which forms part of what is called the resonant primary tank circuit. The spark gap, shown here as being synchronous, rotary, at 1800 RPM. We'll cover why that is significant. It's drawn here schematically as just a simple gap. And the spark gap's purpose and sole purpose is to act as an on-off switch. The primary inductance of the Tesla coil indicated as L1. The secondary, which is to the right of it here, I should use a pin to point. This would be the secondary coil. And in this case, we're looking at a quarter wavelength coil, regardless of what the physical length of the secondary is. One end grounded, and here representing a capacitive load. So there is a distributed capacitance about the winding itself. There is also what is called a terminal capacitance. Back around 1968, I started experimenting with things other than small brass balls or copper spheres or whatever, or just a metal rod on the top of a Tesla coil. And I soon found out from borrowing what is called an aluminum oblite from my Morrison-Lee Van de Graaff generator. How many people heard of Morrison-Lee before? Yeah, we have a few. So that's a combination of a sphere and a toroid, which they called an oblite. And I put that on top of my secondary, which detuned the coil completely. So I started playing with the amount of inductance in the primary and the amount of capacity in the circuit. And lo and behold, I had a bigger output than I ever had before. And then suddenly, having remembered some of the things that Tesla wrote about in his diary notes as well as in his lectures, I began to understand the relationship between a capacitive load for the output of a Tesla coil and the size of the capacitor and the amount of inductance in the primary circuit. Then I started experimenting with the physical relationship of primaries and secondaries, the coupling coefficient of the transformer. Again, looking at the waveforms here, here's our 60-cycle input waveform. That would represent 1/60th of a second, or two 120th of a second periods, one going positive and one going negative. Commutation points, as shown here, refer to the points along the AC sine wave that the spark gap of the Tesla coil is firing. When you run a synchronous rotary gap, that means that the speed of the motor, and therefore the rotary electrodes, are physically timed. There is a relationship between the input sine wave and where the spark gap is allowed to fire. This implies that you can transfer a maximum amount of energy from the transformer into the capacitor and from the capacitor into the primary inductance over here, which is vital. Non-synchronous high-speed rotary gaps are also a device that have their special application. This coil system here that we'll be demonstrating operates with a high-speed non-synchronous rotary gap. What I want to tell you about a synchronous rotary gap is that that gives you one mode of operation of a Tesla coil. If you run a high-speed non-synchronous gap, which is what Tesla experimented with, you will find, we're ready to turn this off now, and we'll move this back into position for the slides. You will find that you can get many different modes of operation, notwithstanding that there is a natural resonant frequency or period for whatever coil system you're operating. How you excite that coil is what makes a difference in its performance. All right. We're going to go through a series of slides here which will further explain to you what I'm trying to say about spark gap design. Now, to begin with, this picture that you see here, can we turn these lights off here in the foreground so that the slide can be seen better? Can you all see that okay? Maybe we can dim the rest of these lights back here as well. Can you people in the back see okay? Okay, very good. How many people recognize this picture? Anyone? I see a couple hands go up. I always begin my slides with this particular slide because it is historically very significant. This is the Tesla coil at the Griffith Park Observatory in Los Angeles. It is a coil that was built during the heyday of Tesla coil construction by experimenters, built by Earl L. Ovington and owned by Dr. Frederick Finch Strong, who was a practitioner of medicine, a member of the AMA, And in the 30s and in the 20s, high-frequency, high-voltage electricity was used extensively for electrotherapeutics and for treating patients, everything from carcinoma to acne and everything in between. And interestingly enough, a lot of that kind of science is coming back now. And the AMA is starting to take note of what took place back in those days as being valid and not just quackery. This coil was used as a demonstration coil by Dr. Strong in his lectures, and then was donated to D.W. Griffith, whose namesake is the observatory in Los Angeles. This was my first introduction to Nikola Tesla and to Tesla coils, circa 1956, as a young boy. And I saw this with sleepy eyes one night as my parents took me to the observatory, and I was completely enthralled, and I decided, I have to know more about this. I want to build one of these. So you could say I was sort of bit by the Tesla bug. Next slide. This is a diagram representation of electric lines of force across a very simple stationary spark gap with two spheres. What I want you to visualize in your mind is the relationship of the design and construction of a spark gap as opposed to what are the electrical lines of stress across that gap. Next slide. As you can see, if you go to needle points, the lines become much more concentrated and coherent. So the ionization process, or the manner of the gap breaking down, would break down at a much lower voltage using this type of a gap as opposed to the previous slide. Next slide. If one were to go to parallel plates, you have more or less a uniform potential gradient of electrostatic lines of force, assuming that the plates are perfectly parallel and smooth. This implies a more uniform operation of a stationary spark gap than either of the two previous types. Next. What happens in a spark gap must be studied microsecond by microsecond. And consider each microsecond of real time of the operation of a spark gap to be infinite time. This diagram here represents just a simple stationary gap. And what you see is an illustration of clusters of electrons. Now, when the gap is healed or is not commutating, or that is to say that there is no spark across the gap, you have more or less a uniform field of free electrons in the atmosphere. As the gap is polarized or is charged up, these electrons start to create bonds, the same way as natural lightning does. That is, they will form, using fractal type theory, links, which you might call minute step leaders, just like in a lightning bolt process. And finally, when they all link up together, you say that the gap is ionized, the gap fires, or a spark takes place, and therefore you could say that the gap has commutated a discharge. Next slide. What happens, though, regardless of the material that you're using or the design or shape of the gap, is that after the gap has fired, there will still be clusters of electrons that are in groups. And one needs to try to visualize this in order to understand why certain gaps work better than others. Next slide. Even long after the gap has fired, remember we're taking time down to less than a microsecond of real time. So after a single spark across a spark gap, there are still electrons that linger or cluster near the surfaces of the electrodes. And this is especially true if the electrodes get hot, because heat promotes ionization at a lower voltage level than if the gap is cold in terms of temperature. Next slide. This represents the difference between free electrons that are associated near the surface of a cold gap, as seen on the left, and a hot gap, as seen on the right. Again, this is very important. When you build a spark gap, you must always keep it cool. The cooler, the better. Next slide. Another relationship to bear in mind, along with what we're discussing here, is the size and shape of a gap. Using the simplest form of a spark gap, which would be just a single stationary gap, the performance of the upper illustration is less efficient than the performance of the lower illustration. The dimension d is variable as a capital letter. The small dimension d would be the cross-section of the electrode material itself. The performance of the lower illustration would give you superior performance, and therefore I say superior commutation of the oscillatory spark discharge because of a broader surface area and a larger mass of material. So it matters not whether you're using steel, tungsten, copper, zinc, whatever material you want to use. It's better to design a gap that is shorter in distance and broader in cross-section. It promotes what is called quenching, which is that the discharge will go across the gap and extinguish quickly so that the gap deionizes or opens more rapidly, and that is important. The operation of quenching is a key element to the performance of any spark gap. Next slide. Of course, Tesla knew this, and if you are familiar with lectures, patents, and articles, the book, Colorado Springs Notes, these next few slides will be very familiar to you. Tesla understood the relationship between having a spark gap that commutated efficiently and then quenched thoroughly and rapidly after each spark commutation. One approach that he took was to have spheres held in stationary electrodes that could be rotated manually such that the surface would always be smooth and polished. And you see the poles of what looks like an electromagnet forming a strong magnetic field across the gap. There are many ways to quench a spark gap. Large surface area and material remaining cold is the simplest way. A strong magnetic field is another way. An air blast would be a third way. Next slide. Another illustration of a strong magnetic field across a stationary spark gap. These are original Tesla illustrations taken from his publications. Next slide. This is very interesting. It's a departure. Tesla experimented with alcohol and hydrogen using a gas to promote the quenching action after the oscillatory discharge. Fairly effective for low power coils, but not for high power. Next slide. Here's an example of a series of stationary electrodes in a channel which then could be subjected to an air blast in order to promote quenching. Again, an original Tesla illustration. Next slide. This is the only diagrammatic representation I have ever seen of what Tesla considered to be his ultimate gap. I would love to go to the museum in Belgrade, assuming everything is still there and still intact after all of this warfare in the region, and I hope to God it is, to see if there is further information in his notes. This represents the illustration of the gap that he used right here at Colorado Springs in 1899. You'll notice that there is a rotary gap. It's contained inside a box or an enclosure, a pair of metal rods, and notice that the points on the rotor are very fine, and quite a number of them. The rods, a very thick, dark material. And notice also that there is a separate ball gap on either side. So we have essentially 1, 2, 3, 4 gaps in series. 2 stationary gaps, balls of unequal size, and the 2 rotary gaps itself. This, he felt, was the optimum representation of an efficient, high-speed, non-synchronous rotary gap. And he makes note of that, but he doesn't go into an exhaustive study about this gap's performance with his equipment, which is one of the curious things that I find about his Colorado Springs experiments, along with the fact that there's precious few documentation evidence of the discharges being 135 feet long off of the mast and so forth. Next slide. This is an illustration taken from an early wireless publication. A stationary single spark gap, good again for low power. Notice the cooling fins, the idea to have thermal conduction of heat. The spark material itself being fairly large in cross-section and flat-surfaced and made of zinc. Spark discharge affects different metals in different manners. Tungsten, I have found, thoriated tungsten, 2% thorium, tungsten alloy, works just about the best for what you can use today. Zinc has been a material that's been used since the days of early wireless telegraphy. Again, the whole idea is to keep the gap cold and cool so that it discharges, it commutates, and then it deionizes or heals or opens, all the same terminology. Next. Here's an example of a commercially made stationary spark gap with copper hexagonal main members and then surfaces that are reduced in diameter but made of thorium tungsten. This is a gap that was taken from, of all things, ladies and gentlemen, a TIG welder, tungsten inert gas. People ask me often, well, what use is a Tesla coil today, and where do you see Tesla coils used in industry? They're everywhere. They're everywhere. A modified form of a Tesla coil, you could say, is a hybrid version of the high voltage power supply in every computer monitor, in every TV set. It's the source of high voltage. It's a high frequency oscillatory circuit. Yes, it uses a ferrite core, so its coupling coefficient is quite high, but the principle of operation is still the same. In a TIG welder, you have argon gas, you have a tungsten electrode, and you have the typical arc welder, which would be like DC or AC and fairly high current and fairly low voltage, maybe not more than 75 volts. But to initiate the ionization process, writing piggyback or multiplexed across this high current, low voltage is a spark gap Tesla coil circuit. And when you first strike a TIG welder, when you start a welding process, you'll see a blue-white spark that may be up to a ½ inch in length. So there is a primary and a secondary that's part of the high current transformer assembly, and there is a capacitor and a spark gap. And this is a spark gap from a TIG welder. It works very well for low-powered coils up to about a ½ kilowatt in input power. So that's an example of where Tesla coils are used commercially in welding, in TIG welders. Next slide. Another example of spark gaps, here's that same small stationary gap in the foreground. You see a pair of sphere gaps in the background. The gaps in the background would be most suitable as a safety gap. I do not recommend this for a Tesla coil as a primary circuit spark gap. Next slide. An illustration again from an early wireless book showing one design of a non-synchronous high-speed rotary gap where there are just 2 rotary electrodes on one common member and many stationary electrodes on a periphery of a ring. Next. Another example. It's amazing how people have taken Tesla's ideas and evolved iteration after iteration after iteration. Notice that they're sharp points. And we have 5 rotary electrodes and 4 stationary electrodes. The relationship mathematically of that versus the charging frequency and the speed of the motor produces what is considered to be an audible sine wave tone. One of the key elements in wireless telegraphy that everybody was searching for was something that at the receiving station sounded like a pure tone rather than just a crashing sound or a crackle. Because of course we're talking about Morse code, CW. So if you could hear a 500 cycle note or an 800 or a 1000 cycle note, that is more audible over a longer distance than just the sound of a static crash. Next. Another example. This was an Acme gap. 2 stationary electrodes, and notice the rotary wheel, and notice the flat surfaces on the rotary wheel for each electrode. Here's an example of where people started to experiment and understand what is called dwell duration. That is the period of time for each spark to take place. How long? Next slide. Cross-view section of that. Notice the flat surfaces now as relation to the previous picture. The idea that the motor was a fixed speed motor. So you wanted to be able to adjust the dwell time. This was not adjustable except by speed. We're going to cover that with this apparatus that we're going to demonstrate. The idea that as speed or velocity goes up, you can visualize that the amount of dwell duration time per rotary electrode passing by the stationary electrode goes way down. So the pulse repetition frequency or commutation rate goes up and the dwell time goes down. There's an inverse relationship there. Next slide. Can we focus that a little bit? There we go. Illustrations of different designs of rotary gaps, and at the bottom, a quenched gap. Multiple stationary flat elements. We'll talk about that further. Next slide. Here's an example of a rotary gap that was built by a friend of mine. You can see the wheel, gray in color. It has 4 electrodes at 90-degree centers around the periphery. Notice the stationary electrodes are crescent moon-shaped metal bars. Way too long of a commutation time, unless you were going to spin that wheel at 20 or 30,000 RPM. He found out very quickly that this design was not effective for Tesla coil work. Next slide. By contrast, here's a commercially made rotary gap. This was originally taken from a radar pulse forming network test system. Many of you will recognize this gap as being used in some of my previous demonstrations, including the one last summer. So here we have 2 rotary electrodes and 4 stationary electrodes. And the electrode material, again, is tungsten. And those rods are 3/8 of an inch in diameter. And you'll notice that they're rounded, and also that the rotary electrodes as well as the stationary electrodes are canted towards each other. So there's a striking action, like striking a match in a matchbook, so that the dwell time is kept very short, even though that the speed of the rotor is only 1,800 RPM. Next. An example of an enclosed rotary gap. The enclosure to do 2 things: eliminate the noise, which will make you deaf, and also to cause nitric oxide, which is generated when any spark gap fires, to add the quenching action. Oxygen promotes burning. You don't want oxygen. You want some inert gas material, hydrogen, nitrogen. Esoterically speaking, the high-speed boys and the high-power boys work with sulfahexafluoride, SF6. Commercially, a quench gap and this form of rotary gap have the same advantage of operating on nitrous oxide, which is generated after the spark is run for a while. Next slide. Another version of a synchronous rotary. This is a Telefunken gap. This is circa about 1922. Next slide. Here's an example of a synchronous rotary gap. There are 4 stationary electrodes, 2 in the foreground and 2 in the background, 2 uppers and 2 lowers. So it's firing across 2 gaps on the near side and on the back side, and you can see that there are 12 stationary electrodes. They're faced with tungsten. The motor runs synchronous at 1,800 RPM or 3,600 RPM, depending on the mode of operation I want to use. Next slide. Closer up view of that. You can see the upper electrode supported by an aluminum bar, and that rod is a solid 1/2 inch diameter of thoriated tungsten. You can see the lower gap too, just about center bottom of the screen. There's a reciprocal gap of the same design on the other side, so it's actually 4 gaps. It has worked very effectively for power levels up to and including 15 kilowatts input. Next slide. Again, an illustration taken from an early wireless publication showing in the upper left a rotary quenched gap, sealed, and where you have a stationary coaxial ring and a rotary coaxial ring. It turns out that Tesla also designed enclosed rotary quenched gaps. So it's actually true that he is a pioneer in many ways. These people like Ben Wood, Ajax, gosh, I can't name you all the names, Murdoch, these are all names going back to the teens and the 20s as far as wireless telegraphy is concerned. Marconi had a rotary gap named after himself, a Marconi-style rotary gap. But in actuality, Tesla pioneered all of that. Next slide. A cross-sectional view of an open-air, semi-quenched gap. The material being made of copper with built-in cooling fins and a very broad flat surface and a very narrow gap. Next. An illustration of a multiple segment quenched gap. Now, ladies and gentlemen, when it comes to efficiency, remember, as you rise in power and as you rise in efficiency of the spark gap, single element stationary gap, close spacing, broad flat surfaces, material that stays very cool. One step better than that, multiple elements in series, where the gap is fairly small. A step up from that, a rotary gap, non-synchronous, variable speed, so that you can adjust the point where you get the best operation. There's many things that go into that, and we're going to demonstrate that element during our demonstration segment in just a short while. A step better than that in efficiency, synchronous rotary. Want to go even more efficient? Go to a quenched gap. Unfortunately, it's very difficult to machine and design a quench gap that can accept very high power and will not burn up on you in a short period of time. Next slide. This is an example of a Telefunken quenched gap. Notice the motor on the left. The trough that those discs sit in forms an air chamber or a manifold, such that cold air can be blown in and radiated up through the cooling fins of each element to try and keep it cool. This gap was rated at approximately 2 kilowatts power, and this was typically used on board ships from about 1923 through about 1928. Very efficient, but every once in a while you'd have to disassemble all of the elements and clean them, because of the nitrous oxide would contaminate the insulating discs and also the surfaces of the electrodes. But with this design of gap, you have maximum quenching, maximum commutation rate, and maximum power transfer from the energy stored in the capacitor into the primary. You want to hit that primary with as much oscillatory energy as you possibly can. And at the same time, you don't want the discharge to continue past the initial pulse. You want a highly damped waveform in the primary, which will help to promote more of a continuous wave current waveform in the secondary. And if you pack those pulses close enough together, you end up with almost a CW output on your secondary, which translates into higher current. And the nonlinear relationship of spark gap length versus voltage plays an important part in that. Because whereas you may have a certain potential voltage on the output of your Tesla coil, as you raise the current output, irrespective of the voltage, the spark length gets much, much longer. And we'll cover why that is true in a short time. Next. Cross-sectional view of a homemade quench gap. Aluminum discs, you see the phenolic spacers, that's about 5 inches in diameter. A gap like this could be run for maybe 30 seconds at a couple of kilowatts AC input. Then it would heat up to the point to where it would be ineffective. The heat on the surface of the sparking plates inside these chambers would be so hot that even though there's nitrous oxide for an atmosphere, the radiant heat of the gap would still promote that lingering ionization that we talked about from those previous slides. Next. Another example of a quench gap homebrew. Stainless steel, 1/4 inch. This gap was very effective. I could run this gap up to about 10 kilowatts for about 30 seconds before it would go away. You could just see the spark discharge diminish. Next slide. We're going to switch a little bit now to another topic. Primary of a Tesla coil, flat spiral or Archimedean spiral. The coupling coefficient between a primary and a secondary is as important to a Tesla coil design as is the spark gap, as is the capacitor, as is the material that you use for a capacitive load on the output. All of these elements are so simple on paper, but there is such a vast variation, so many iterations, that striking or landing on the right combination is the most difficult thing to do. And the mathematics that go into the coupling coefficient between the primary and the secondary, you say, well, all right, I've got this primary, I've got this secondary, I'll get this capacitor, I'll use this much current, I'll put in this much voltage, I'll use this kind of a spark gap, and everything's going to work perfect. Wrong. What you need to do, and bear in mind, is take one variable. Take the coupling coefficient, the design and the spacing between the primary and the secondary, the size and shape of those coils, and vary only one element at a time, and go through a parametric study, an investigation, and then build upon that step by step. Next slide. This coil in operation produces a handsome display, but it's very inefficient. The top of the coil was topped with an aluminum disc. The point of that was to eliminate the chance of wire burning near the top winding. This is what you call the Band-Aid approach, and it was commonly used in Tesla coil articles of the 20s and 30s. Notice all the corona coming off of that top plate. That's lost energy. You don't want it there. You want it up on top of the discharge electrode. And just like in the cases of the Griffith Park Observatory coil where you saw the ball with the 2 corona points on either side, this coil, which belonged to Dick Arant, or Richard Gibson Arant, who many of you know, wrote many articles for the Tesla Coil Builders Association, was fashioned after the Griffith Park Observatory coil. He too got bit by the Tesla bug, and his case was about 1938. Shortly after the coil was first installed. Well, he couldn't find a conical coil for him, so he built this. Next slide. A closer-up view of that discharge. Again, notice the amount of corona coming off the top electrode and the top plate. Lost energy. Those sparks at maximum are about 36 inches long. The power input here is about 2 kilowatts. Next slide. Here's that coil in full activity, running at about 3.5 kilowatts input, and I've set up a grounded electrode to the right. Notice the difference in the characteristic of the discharge. The free air corona is lavender purplish in color, and the sparks going to the grounded electrode are brilliant white or blue-white. That is a signature, ladies and gentlemen, of how you can judge the amount of current output of your coil. If you get really blue-white hot sparks, you know that you have a lot of current. If you get sparks that are lavender purplish color, even though they're going to a grounded electrode, that is indicative of lower current. And again, that has a direct implication on this nonlinear relationship we want to cover further. Next slide. Turns out that you can do a lot of things with just a few simple pieces of hardware. Here's that same coil with a toroid placed on top. Notice that there's only corona coming off the one point. And now the gap is out, instead of 3 feet, it's out 5 feet. Same power input, no change in tuning, just a better capacitive load and a way of distributing the electrostatic field out away from the secondary. So notice the top plate, just underneath the toroid, just a faint glow, no sparks coming off of it at all. That's because the E field has been moved out to the circumference or the equator of that toroid. Tesla understood this, and he employed this in his patents and also in his designs at Colorado Springs and again at Wardenclyffe. Next slide. An example of a sympathetically resonant coil is on the right, driven by the same coil seen in the previous slide on the left. The gap here, approximately 7 feet. This is just a brief pulse of operation at about 3.5 kilowatts. Next slide. Notice what we have here now. See the corona on the ball to the right, with the corona going straight up vertically. That is influence from this coil with only a ground connection in between. So you could say that the coil on the right is a freely excited resonant helix. Notice also the webbing or the texturing of the free air corona from the driving coil on the left versus that of the coil on the right. You can also observe corona discharge and get an approximation on frequency of operation by looking at how many tendrils or individual corona streamers there are in the operation of a coil. Next slide. That coil again in full activity, and it's interesting that this picture sort of mimics a very popular photograph that was taken by Mr. Ray Alley while Tesla was seated in a chair, and the caption reads, "Coil in full activity, striking a non-connected coil 22 feet away." Most of you recognize that photo. Notice the similarities of the signature of the discharge in this photo compared to what Tesla did here in Colorado Springs in 1899. And if you look closely, you'll see that there's a purple sheeting or hue in between the individual streamers that strike the coil on the right. Notice again the corona from the ball on the coil on the right. Many, many fine textured tendrils as compared to the streamers from the driving coil on the left, which are much more defined and fewer in quantity. Again, this is a way of telling the difference between the resonant frequency of the coil on the right as opposed to the driving coil. It just so happened that they were resonant, but they were operating on different frequencies. Next slide. Here is an example of a Tesla coil built years ago with a helical primary made out of copper tubing. The secondary is about 20 gauge wire. There's about 450 turns, and that's a sono tube, a cardboard tube that's first been treated with shellac and carefully dried, and then wound with a PVC-coated stranded wire. Now that toroid on top is the same size as the one I'm pointing to right here. But you notice the difference in the size of the coils here, and this extra coil that I'm pointing to here is compared to that secondary. Now that's just a single primary and a single secondary, like any standard Tesla coil. Next. Closer view of that primary, 3/8 copper tubing. Next slide. The operation of that coil. Notice that the streamers are now much more coherent. They're fewer in number. And you can see the difference between the free air corona as opposed to the power arcs that attach to the ground or to the siding of that structure. Next slide. Another example of that coil in operation where a corona point is put up to direct the discharge. Next. And the coil operating at maximum power where that particular arc is approximately 7.5 feet long. Next. I always show this slide too, ladies and gentlemen, because when you build big Tesla coils, one needs a suitable source of power. Next slide. This picture is a vintage picture of yours truly with the obligatory signature sweatband and what I refer to as my Model 10 coil. This coil presently resides at the Battelle Memorial Research Institute in Columbus, Ohio. Notice that it has a helical primary and a helical secondary. The secondary is a fiberglass tube, 24 inches in diameter and just over 9 feet tall. There's only 400 turns of wire on that coil. It's number 10 gauge wire, number 10, stranded, plastic insulated, running about 2.5 turns per inch. Next slide. A close-up view of the primary. You notice the black cable here in the foreground, that's welding cable. 1.25 inch in diameter welding cable. And after 30 seconds of operation, that cable gets so hot you can smell the rubber burning. That's the kind of power that's oscillating in that primary circuit. Next slide. A brief shot of that coil set up in my backyard high voltage laboratory at RF Gulch. Notice the people in the background are huddling underneath the garage door. The toroid on top is 4 feet in diameter and 1 foot in cross section. Next slide. Here's what happens when you don't have a coil properly tuned and you're running at high power. Even though the toroid is in place, which should take the electrostatic field and deflect it out to the equator of the surface of the toroid, if you have it improperly tuned, you could get a corona coming out in spite of it. That did considerable damage and caused me great heartache. Next slide. When it is properly tuned, it is possible to get some very handsome sparks. Again, notice the difference here. This is about the same time exposure as the other pictures you've seen, and yet at the same time, these tendrils as free air coronas are very well defined, and there are fairly few of them in number, and those that are clustered together are very thick. That's about 15 foot of discharge rising up vertically from a small corona point placed on top of that 4-foot toroid. Next slide. Taking that same coil and hooking up a transmission line to it, much in the same way as this aluminum tube right here I'm pointing to is a transmission line between this coil and this coil. I performed an experiment. It was for a videotaping of a program called That's Incredible. How many people remember that program? 3.5 hours of taping, and it was reduced to 6.5 seconds of airtime. And I burned out 2 capacitors that night. The lights that you see set up over there, those are studio lights that they brought for the occasion. And what I have is I have that same coil you saw on the previous slide, and it's hooked up to a big transmission line that I've got suspended with ropes and tubes and everything else to try and get it way up above the ground. And it terminates with what you see as like a ball that's brightly illuminated over the pool, the swimming pool. That's about a 14-foot gap from the bottom of that ball to the pool. Next slide. Here's what it did. That's 1/4 inch nylon rope, and you can see the corona where that flexible tubing bends down towards the ball. It burned the rope, and yes, the ball fell in the pool. But before it did that, next slide, it produced this kind of discharge. That's approximately 1 second of operation at about 25,000 watts power input. And these arcs were so blindingly bright and so deafening to the ears that my ears were still ringing with tinnitus almost 2 hours later. And just standing and having somebody else hit the switch at a safe distance but at close view, the image burned in my retina just like seeing a lightning bolt at close range for a long time. You notice that where the sparks attach to the surface of the pool, they kind of distribute out, and there's a little orange spot or pinkish spot where it hits the surface of the water. Next slide. Okay, that's the end of the slides, ladies and gentlemen. What I want to do now is I want to move into the demonstration phase of this presentation. We'll move along quickly here. May I have these lights up forward, turned back on, please? And we need to turn the projector off and move this out of the way. Okay. I want to describe this equipment to you. This is the first in a series of magnifier Tesla coils. Magnifier is a term that is applied to a 3-coil system. Tesla referred to the coil he built here in Colorado Springs as a magnifying transmitter. And he talked about the concept of magnification of oscillatory energy and processing of power, as in power delivery. Well, power delivery implies a relationship between time and usable real power, as in amperes and voltage. And he realized that in order to attain the kind of performance that he was looking for, he could not do it with a simple 2-coil system, that is, a primary and a secondary resonant transformer. He evolved the idea of a 3rd coil, a separately tuned helix that would sympathetically or symbiotically be related to the primary-secondary traditional Tesla coil. These are all air core transformers, just like any standard Tesla coil design. Here is your standard Tesla coil. Flat ribbon, primary winding. Here's the tap point. It's running approximately 1, 2, 3, almost 4 turns of inductance. The secondary. Notice the form factor on this. It's almost as big in diameter as it is tall. When we say form factor, we talk about length of winding as opposed to diameter of the winding. One mistake that often is made by Tesla coil builders is that they build a coil that's too skinny and too tall and it's wound with too many turns of too fine wire. You don't need to do that. And here I am, and you're looking at this saying, yeah, well, what's he talking about? What's this thing right next to him? This is an exercise in what Tesla talks about in one of the most important patents that he ever applied and was granted by the U.S. Patent Office. If you look at that illustration, it will show a very tight couple between 2 turns of a primary and just maybe a half a dozen turns for a secondary. And then you'll see what looks like a transmission line, a connecting link, and then it'll show the extra coil as being tall and slender with many turns, and it'll show a huge capacitive load on top of it. Well, there are other people who are experimenting with this and being very successful with it. And I especially want to make note of the work that Richard Hull is doing with what he calls TCBOR, that is Tesla Coil Builders of Richmond, Virginia. Because Richard is building magnifiers back on the East Coast, and he's doing extremely well with them. In fact, I've seen a video of a coil where the coil itself, the extra coil, is only about 1 foot tall, and it's only about 2 inches in diameter. And he has this huge capacitive load on top of it. The thing looks like it must be 3 foot in diameter and maybe 5 feet tall. It's on top of a big insulator, and it's driven from a small coil just like this. He's getting over a 5-foot-long arc off of that ball. And the secondary is only 12 inches tall. And you say, well, my God, how can he do that? How can the insulation stand up to it? How can you have a coil that's only 1 foot tall put out a 5-foot-long arc? Electrostatic deflection and how the coil is tuned and being driven or kicked by the primary-secondary combination that's feeding it. This is an exercise in the same genre. I hope to next year bring to the 6th biannual International Tesla Society Symposium and Conference what I call Model 14. How many people saw Model 12 operate last year? Quite a few of you, okay. That was Model 12. Model 14 is going to be the next in a series of magnifier coils. This is the first one. I call it Model 5M. Real original. Okay, we have 4 capacitors down here. They're all in parallel. They're each 0.02 microfarad. The rotary spark gap on the back side has 8 rotary electrodes, 2 stationary electrodes, cooling fins made out of brass, and they're all faced with tungsten. Over here, the power supply transformer. This is a potential transformer rated at 1500 volt amp, or 1.5 kVA. The beauty about these is that they will withstand very high RF feedback voltage without breaking down the insulation, because they're rated for typically 110 kV BIL, or 110,000 volts basic impulse level. That implies that the quality of insulation on the secondary coil or the high voltage winding of that transformer is very good. And it is a non-saturable core transformer, meaning that you have to use some external means of limiting the input current to that device, which is what is on that platform over there. 2 variacs, one is a legitimate auto transformer for voltage control, and this gentleman right here knows what I'm talking about because we talked about that over breakfast. The other variac used as a series variable reactance, but it's not just current control, because what you're doing, this is a complex impedance that transformer is seeing. Inductive capacitive, inductive reactive relationship. Power processing, which Tesla understood, means that power is going one way. It goes right back to the analogy I brought up in the beginning of this talk about ham radio operators who go for a low VSWR. They try to have a flat transmission line, quote unquote, between their transmitter and their antenna. Get the power out to the antenna. Don't let it be lost in the transmission line. Don't let it have it come back into the transmitter and burn out your bottles or your solid state finals. Make that power go that way and be usable. Same thing here. So what you're doing is you're changing the current phase angle with respect to the voltage phase angle. And that implies power factor correction, and that implies adjusting for maximum forward-going power into the Tesla coil. Okay, we've described the equipment. This is an extra coil, a phenolic form. This is 19-gauge wire. There's approximately 500 turns. It's close space wound, ladies and gentlemen. It's not a spaced winding. It has several coats of flectovarethane, or polyurethane enamel insulation on it. You notice this is a 14-inch diameter toroid here. It has the same cross-section as that toroid back there, 5 inches. This is here only for show. All I need to do is have this thing up off the ground so I could use anything that would be suitable. But when you build Tesla coils, you like to have a little artistic touch to it. So I had this insulator for years, and damn, that's a nice insulator. I love that insulator. I got to find a good use for it. And I'm scratching my head trying to figure out what I'm going to bring to this conference and talk about and demonstrate. So 2 weeks ago, late one night, just as I was nodding off to bed, I've got it. I'm going to build a magnifier. So I called Tony and Rosalie up on the phone. They're going, oh no, you're going to do what? So I designed and built this, and I applied the knowledge that I had gained, plus what I had learned from Tesla, the true master, the only master, Nikola Tesla. And I thought, well, I can vary the length of the transmission line. I can vary the amount of input capacitance. I can vary the output capacitance by changing these electrodes. This I'm stuck with because once I build it, that's it. Unless I want to start ripping off windings, and I don't want to do that. Over here, I can change the amount of capacitors. I can change the amount of inductance. I could also change the size of this capacitive load. Whew. Fortunately for me, it all worked. We're going to demonstrate this for you now. And I'm going to demonstrate commutation rate versus pulse repetition frequency versus dwell duration. That is the period of time for each oscillatory discharge to take place. And at this point in time, we're going to turn off the sound system because, like Murphy, I don't like to take any chances. And those of you who were at the conference last summer at the Cheyenne Mountain High School will remember that the Van de Graaff generator that was on stage, when fired up and it zapped the microphone on a mic stand, took out the mixing board, and the gentleman back here in the corner, they didn't want to talk to me for a while. It was the final night, Saturday night, the 7 p.m. show, so we did it vaudevillian style. And I was out there on stage trying to project and enunciate, hey, in the back, can you hear me back there? The audience was half asleep anyway, but that's okay. And we had a good time. So we're going to do the same thing now. I'm going to turn off this microphone, have the gentleman turn off the sound system to save his equipment. We'll start this demonstration by operating this Tesla coil, driving this extra coil, and as you can see, I have a corona point placed right here. And you'll see this operation. The maximum power input I'm going to put into the system, ladies and gentlemen, is approximately 3,500 watts, or 3.5 kVA, or 3.5 kW. You will see how it is possible for such a small coil to excite a resonant, shock-excited helix and produce a very large discharge.
Yeah. Probably if you want. Okay.
And I'm going to bring up the high voltage very gradually. Since this motor is a AC brush motor, it takes a few moments of time for it to build up enough inertia so that it's up to the proper velocity. And I'm running this motor on a separate variac so I can vary the speed of the motor. Here we go. Oh! Feel how hot the tip of that rod is. What a curve here. You need that up like that. Very tip. Feel how hot that is. Another thing that you can do with a magnifier like this, I'm going to use a much smaller corona point, just a brass circle. I'm going to place it out here in front. We'll run the coil like this.
gauge wire. There's only about 175 turns here. This is a PVC form polyvinyl chloride, 10.5 inches in diameter and about 18 inches tall overall. And because of the relationship of the spacing between this coil and this coil primary, the mutual coefficient of coupling is very tight. In fact, it's beyond critical coupling. So if you were to look at it on a spectrum analyzer, you would see two separate waveforms with a hump in the middle. Those of you who do RF design work will understand what that means. That there's a lower side band and an upper side band, either side of a center carrier frequency, or resonant frequency, which is what's hitting this. I have here in the ground connection a 150 watt light bulb. I'll bring this over and just short it out here and ask Tony to bring in the voltage control. You have to turn the switch on first. Make sure you got it. This is grounded. Okay. That's 150 watts of power on that coil. And yes, the bulb is hot. Of course, with a smaller amount of power for an inductive load, we could very easily light a 40 watt bulb at much lower power. And in fact, to see the spark gap starts firing. Go ahead, bring it up to a word just fire. And in fact, if you bring it up any higher, we bring the bulb out. I'm going to ask my assistant Rosalie now to show you, for those of you who have not seen this before, that it's possible for the RF body to take RF and feel discomfort. She's going to become the resistive load on the series connection of this light bulb. She's going to stand on this makeshift insulator stand. I didn't have enough room or space in my truck to bring a big portion of this stuff.
Jim, I'm going to have somebody standing right in my way.
She's in a kneeling position for stability's sake because it's not a very broad-based feather bar. She's fine. She's not known as the electric lady for nothing. All right, at this time, we're about to 25 minutes to 12 noon. It's time to wrap up this. I will field a few brief questions from anybody who has any, short and brief, and then we will adjourn. House lights, please. Let me say before I take any questions that you saw how I varied the speed of the spark gap, and you saw a difference in the sound of the output of the spark. Plus, you can see a change in the characteristic of how the spark works.
And I want to do that now. There's an article which I would like to call to your attention for those of you who have your notes handy. I have a Xerox copy of it here. First of all, let me say that this is an IEEE publication. It is the Transactions on Power Apparatus and Systems, or PAS, IEEE journal. And this is volume number PAS 102, number 6. This is June 1983. The authors of this paper, two individuals, Mr. F. period Ralph Cotter, K-O-T-T-E-R, of the National Bureau of Standards, now known as NIST, and Mr. Andrew N., as in November, N. period Smith, a consultant from Eldridge, Montana. The abstract reads, measurement of electrical breakdown of both quasi-uniform and highly non-uniform field air gaps at a frequency of 28.5 kilohertz are reported. Gaps between a variety of electrogeometries ranged from a few centimeters to over 2 meters in length. Breakdown voltages significantly below the corresponding 60 hertz or 60 cycle values were observed with electrodes for which appreciable pre-breakdown discharges occurred, and a pattern of anomalous flashovers at considerably lower than normal breakdown voltages was noted with quasi-uniform field gaps. The results obtained appear to correlate well with the data found in the literature for higher frequencies but lower voltages. An annotated bibliography is included. What does all of this mean? It means that these people worked with a high-power transmitter on the Hawaiian Islands back in 1983, and they shock-excited a helix as an outdoor experiment. So instead of an actual Tesla coil, they used a high-power transmitter used mostly for Loran purposes. With the system, they were able to induce, in the ground connection of the helix that was being shock-excited, a RF-calibrated high-current ammeter. So they looked at what is called an IR drop, and they measured the amount of current in that circuit as a means of determining what the output voltage should be. The bottom line, how many people think that at high frequencies, 20,000 volts per inch is a valid measurement value? Reading the article, you will find out that it drops to as low as 8,000 volts per inch or lower. And the reason for this is very self-evident if you stop and think about it. Remember what I talked about with the spark gap and the lingering ionization and the analogy to what people understand about the process of natural lightning, following fractal theory, or chaos theory, if you will, and the step-leader pattern, which is very fast and virtually invisible to the naked eye, that causes an ionized link chain to connect, like boxcars of a train, all finally getting connected together instead of being floating in time and space. And once linked up, forming a low resistance path for a high amount of current to follow through and do a super ionization of that connected channel, meaning the spark that you see. The same thing happens with the Tesla coil, but bear this in mind. As we think in terms of time and space from microsecond to microsecond, the reason why there is this nonlinear relationship is because of those free electrons that are randomly and chaotically distributed about the atmosphere. What happens with the Tesla coil? It's an oscillatory high-voltage transformer. So that means that it's going both positive and negative at what? The resonant frequency of the output of the coil, right? So that means we have equal number of positive and negative polarity high-voltage pushes, if you will, against a chaotic random atmosphere. So these electrons and these little fractal step leaders start linking up. And that happens twice every oscillatory pulse. So irrespective of whatever the frequency is, irrespective of whatever the pulse repetition rate of the spark gap is, you have these electrons that are linking up where this is positive against a negative field, or where this is negative with respect to what looks like a positive field. But there's a finite amount of time for these electrons to travel through air, because air does what? It offers resistance to the movement of anything, including electrons. And it is that movement, that resistance, that creates the ionization, that is the heat, the heating that we see as a spark. you're not seeing the electricity. You're seeing the superheated ionized air channel that the current is creating from moving molecules of air out of its way as it traverses from 2 points. Well, it turns out that with a Tesla coil or any other thing operating at high frequency, much above 10 kilohertz, it turns out to be a general rule of thumb. That's where the nonlinearity of distance versus voltage increases dramatically. And in fact, it's almost a logarithmic curve. In fact, it flattens out. If you get out past the point of running 1,000,000 volts, what you call 1,000,000 volts for a Tesla coil, you could actually have a 10 or 12-foot spark, and it would only be 1,000,000 volts. If there was enough current in that discharge, especially. If the current was quite low, the voltage would have to be considerably higher for the same spark gap and the same distance to bridge that gap. But these electrons, when they go out and go back, they can't cover that long distance in that same period of time. So there's clusters of ionized random spaces in time and three-dimension space that are still, what, at a lower electrical resistance than the surrounding atmosphere. So it's like floating links waiting to be reconnected again. And that's why there is this nonlinear relationship. All those electrons can't go all that distance back and forth in such a short period of time. Some of them are left out here hanging, but still connected as clusters. And that's why I wanted to make reference to that illustration of the spark gap. It turns out it's the exact same process and the exact same phenomena with a spark gap that commutates poorly due to lingering ionization. I call it post-ionization, or that is electrons that are still causing the gap to be partially ionized after the initial oscillatory discharge pulse has been commutated. Same thing here. And that's why a Tesla coil will produce a much longer spark at a lower voltage than what it would require to bridge the same gap with the same type of electrode material at 60 cycles or 1,000 cycles or DC. Lightning. What about lightning? How many volts does it take to create a lightning bolt where the bolt might be 10 or 20 kilometers in length? Not that much. Same process. The step leaders that are going down, that are creating the initial ionized path, are responsible for producing a nonlinear relationship through time and space of the atmosphere where it's connected. And then if the initial pulse of return stroke current is quite high, it can go a much longer distance at a much lower EMF or voltage potential than if the initial current return stroke is of a much lower value. And that's why there's a lot of controversy about what is considered a linear benchmark of measurement nowadays with natural lightning. Tesla coils especially. So I'm guilty of it, and every other Tesla coil builder I've ever met is also guilty of it. We all like to say, this coil's putting out 2.5 million volts. Well, that's a nice thing to say, but can you actually say that in reality? No. It turns out that the only accurate measurement you can do is if you had an electrostatic voltmeter that had infinitely no self-capacitance and infinitely no self-inductance, and you could somehow introduce it into the E field of the output of your coil. Alternately, one could use a current transformer and measure the input current, calculate the IR drop through the inductance to try and determine quantitatively what the amount of current is versus what the coefficient of coupling and the inductance ratio is times the input charging voltage, the effective charging voltage to the oscillatory circuit to try and obtain a valid measurement of voltage. What is the bottom line here? Everybody wants to make bigger sparks, everybody that I've talked to. The question is, how do we quantify what we're talking about? I say the best thing we can do is say, well, I have a coil that makes a 5-foot spark. He has a coil that can make a 7-foot spark. This gentleman has a coil that can make a 3-foot spark. That's valid. The semantics of that are not arguable. But to say, well, my coil is producing 2 million volts, 10 million volts, 20 million volts is a debatable issue. And I hope to, next year, bring you further evidence through experimentation following the article that I cited. And I'll have this copy here for your inspection following this talk to further go into this, because it turns out that there's a lot of relationship between the nonlinearities in the performance of a Tesla coil and the ionization process, which is what the Tesla coil does. At this time, I'd like to say thank you for your patience and your attention. You've been a wonderful audience, and if you have any questions, I'll be happy to answer them now. Thank you.
We
Yes.
will have to cut off the question and answer.
Oh, we do?
Yeah.
Okay.
We won't be able to have a question and answer session right now, but there will be some other times where we can get together more informally for questions and answers. Thank you very much. A couple of quick things. If you have a copy of yesterday's USA Today, which is distributed free to guests of the hotel, on page 6D, there's a article on Alternatives Meet the Mainstream. It's about the Federal Office of Alternative Medicine. And if you have that, save it. We want to try to save up as many copies of that as we can among ourselves so that we can get some copies floating around of that. The other thing is that there is a TV shoot happening right now, and we're going to have to respectfully ask that everybody clear